You know how sometimes a story just pops up, maybe in the news, it feels a little confusing, maybe a bit concerning, and you just think, man, I wish someone would just break that down for me.
Mm,
Well, that's pretty much why we're here.
exactly.
Today, we're going to get into something that felt, I don't know, almost like a Cold War echo. It happened back in the autumn of 2017, all across Europe. These really sensitive monitoring stations started picking up something unusual in the air.
That's right. We're talking about this subtle, but it was definitely persistent increase in airborne ruthenium 106.
Ruthenium 106.
Okay.
Okay.
And you can think of us as like your investigators for this deep dive. We've looked at news reports, scientific info. The Wikipedia entry is actually pretty detailed on this one.
Good source.
Yeah, trying to answer those key questions. What exactly was this stuff? Where did it likely come from? And, even though the official line was mostly low health risk, why did it still cause quite a bit of concern internationally?
Right. So our mission today is basically to unravel that mystery as best we can. We're going to sift through those first reports, look at the evidence that came out later, and really try to understand the most likely sequence of events.
And maybe touch on some questions that, well, still don't have totally definitive answers.
Exactly. So, okay, where did this whole thing kick off? How did scientists even realize something was, up?
It really started late September, rolling into early October 2017. These advanced air monitoring networks across Europe, they started logging these elevated levels of ruthenium 106.
And where are we talking? Like specific countries?
Oh, yeah. We're talking Switzerland, France, Austria, Norway, Greece, Germany, Finland, Slovenia. They all reported detections.
Wow.
So it wasn't just like a blip in one place. It was genuinely widespread across a big chunk of the continent.
That's pretty striking, isn't it? This invisible radioactive trace just popping up on sensors in so many different countries, almost out of the blue.
Mm-hmm.
And it wasn't something that dragged on for ages, was it? It was a fairly tight window.
That's right, yeah. The detections really seemed to start around September 25th. They peaked in that first week of October, and then almost as quickly as it appeared, it was gone by mid-October.
Huh.
Now, here's a really crucial point, just to get the scale right. For most of Europe, the actual amounts they detected were tiny. We're talking microbecquerels, maybe a few millibecquerels per cubic meter of air.
Okay, so really small numbers.
Really small. Think of it like, a single drop in a huge swimming pool. So experts pretty much agreed these levels pose no significant public health risk that far away from wherever it started.
Okay, so a tiny whisper for most people. But didn't some of the analysis suggest it might have been a much bigger deal closer to the source?
Absolutely. That's where the French Institute for Radio Protection and Nuclear Safety, the IRSN, comes in. They
Hmm.
did some really detailed analysis and modeling,
Okay.
and their estimate, a much, much more substantial total release, somewhere in the ballpark of 100 to 300 terabecquerels.
Whoa, okay. Terabecquerels, that sounds like a lot more.
It's a huge amount, yeah. If their calculations are right, that amount would definitely represent a potentially dangerous situation within, say, a few kilometers of the release point.
Dangerous how?
Serious enough that you'd need to think about evacuating people nearby. Just to give you a tangible idea, that amount of radioactivity, it corresponds to maybe 1 to 3 grams of actual ruthenium 106.
1 to 3 grams. Doesn't sound like much physically,
Yeah.
but radioactive-wise.
Exactly. Radioactively, that's a significant quantity. So yeah, a tiny trace far away, but potentially a really big problem right at the source.
Wow, okay. That difference is stark. It really changes the picture depending on where you were, doesn't it?
Hmm.
Which, of course, leads straight to the massive question, where did this stuff actually come from? Finding the origin must have been like a proper detective story.
It definitely was. The first assessments, especially coming out of Germany, they just pointed vaguely eastward, more than 1,000 kilometers away. Not super specific.
Right, east is big.
Very big. But the French IRSN's work, using that atmospheric modeling, really helped narrow things down. They pointed much more confidently towards the South Urals region.
South Urals. Okay, where's that roughly?
It's that area between the Ural Mountains and the Volga River. So geographically, it puts you potentially in Russia, maybe Kazakhstan.
Okay.
And importantly, the IRSN analysis also suggested it probably wasn't a nuclear power reactor.
Oh, interesting. Why not?
Well, the type of radioactive material, just ruthenium 106 and nothing else really significant, and the pattern of the release, it pointed more towards something like a fuel treatment facility or maybe a place that makes medical isotopes.
Gotcha. And what did Russia say initially when all these European countries started reporting detections?
Well, the initial official Russian response was pretty clear. Flat denial. They said no nuclear incidents, no mishaps on their territory that could explain this radiation spike.
Okay, standard denial. Did that change?
It did, a bit later. Their own National Weather Service, Roche-Hydromet, eventually put out a report, and they confirmed they had detected increased levels of beta activity.
Beta activity, that's a type of radiation, right?
Yep, it's what you get when certain radioactive elements decay. So finding that was another sign of unusual nuclear stuff around. And crucially, Roche-Hydromet also confirmed finding ruthenium-106 specifically
Where?
in aerosol samples and on surfaces right there in the South Urals region, the Chelyabinsk Oblast specifically. And this was between September 25th and October 1st, matching the European timeline. They even noted some pretty significant increases at some of their monitoring stations there.
Huh. And wasn't there also a detection way up in St. Petersburg?
Yes, that was reported too, a bit later, in early
Sure.
October.
Okay, so we go from a flat, nope, nothing here, to, well, actually, yeah, we saw some unusual radiation, including ruthenium, in the exact area the French pinpointed. Which brings us, I guess inevitably, to the place that always seems to come up in connection with this, the Mayak plant.
Yeah.
Why was Mayak immediately such a strong suspect?
Well, the Mayak Production Association, it's in this closed city, Ozyorsk. It has a very long, very complex history.
Right, infamous almost.
Yeah, reprocessing spent nuclear fuel, making various radioactive isotopes. Given the type of isotope found, just ruthenium-106, and the suspected location in the South Urals, Mayak just jumped out as the prime suspect.
Makes sense.
But just like the initial government line, Mayak itself and Rosatom, that's the Russian State Atomic Energy Corporation, they also initially denied any link whatsoever to the ruthenium detected across Europe.
But that stance didn't hold forever either, did it? It seemed to evolve.
It did evolve, yeah. By November 2017, the official Russian position shifted slightly. They acknowledged that, yes, their monitoring systems had picked up a spike in radiation.
Where?
At two facilities located within about 100 kilometers of the Mayak plant, right around the time of the European detections.
Okay, getting closer.
Closer, but they still argued the data wasn't totally conclusive to pinpoint the source definitively, and they maintained their denial that anything had gone wrong at Mayak itself.
Right. But then didn't someone from Mayak make a sort of interesting comment?
Yes, that was in December 2017. A senior executive there, Yuri Morkov, he made what you could call a partial admission. He said that, yes, ruthenium-106 is routinely released from Mayak.
Routinely.
Yeah, in what he called insignificant amounts, just as a normal byproduct of reprocessing spent nuclear fuel.
Okay.
But crucially, he strongly denied that Mayak was the source of this particular much larger spike that Europe detected. So routine small releases, yes. The big 2017 event, no.
Okay, so we have this strong geographic link pointing towards Mayak. We have denials of responsibility for the big event, but an admission of routine smaller releases. This seems like where the science of nuclear fuel reprocessing gets really important to sort of connect the dots, right?
Exactly. This is where we need to get slightly technical, but it's key.
Okay, let's do it.
We need to talk about the PureRx process. It's the main chemical method used worldwide to separate out the useful stuff, uranium and plutonium, from spent nuclear fuel.
Right.
Now, normally in this process, the ruthenium that's in the spent fuel exists as a metal. And metallic ruthenium has an incredibly high boiling point. So under normal circumstances, it's very unlikely to become airborne in any significant amount.
Okay, so it should stay put.
But there's the intense radiation from the spent fuel itself. This radiation can mess with the chemicals around it, things like water and tributyl phosphate, which is used in the PureRx process.
That's with a mouth.
Through something called radiolysis. Basically, the radiation breaks down molecules and can create highly reactive chemical conditions. And under certain conditions, this can lead to the formation of a different ruthenium compound, ruthenium 8th oxide.
Okay, a different form. And that matters because
Because this oxide form is much more volatile. Its boiling point is way lower, only around 40 degrees Celsius, like a hot day.
Okay. Much easier to turn into a gas then.
Exactly. And it's also a strong oxidizing agent. So this chemical transformation provides a plausible pathway for how ruthenium could actually escape and become airborne.
That makes sense. So not impossible, just needs specific conditions. And hasn't this sort of thing happened before? Our sources mentioned a historical case.
Yes, absolutely. There's a well-documented incident from 1973, the B204 incident at the Sellafield reprocessing plant in the UK.
What happened there?
During a reprocessing run, there was an unexpected chemical reaction, sort of a backflow, and it generated radioactive gases containing ruthenium-106, which were then released into the facility. 34 workers were exposed.
Wow. So it definitely proves that these kinds of airborne ruthenium releases can happen accidentally during reprocess.
Precisely. It's not just theoretical.
And I think you mentioned something about the timing of reprocessing also being important, like how old the spent fuel is.
Yes, that's another critical piece. Think about those older British plants, the ones that processed fuel from Magnox reactors. They had to reprocess that fuel pretty quickly after it came out of the reactor, maybe just a few months later,
Why so fast?
because the cladding around the fuel rods, made of magnesium alloy, could corrode if left too long in cooling ponds. But reprocessing fresh fuel like that means you're dealing with stuff that still has a lot of relatively short-lived radioactive isotopes in it,
Including ruthenium-106,
including ruthenium-106, which has a half-life of only about a year.
meaning half of it decays away each year.
Right, so fresh fuel has much more of it. Now contrast that with most modern reprocessing plants, like the La Hague facility in France. They typically wait maybe around a decade before reprocessing spent fuel
Why wait?
to let isotopes like ruthenium-106 decay away significantly. Waiting reduces the amount present and therefore reduces the risk associated with potentially forming that volatile ruthenium oxide. So processing younger, less aged fuel inherently carries a higher risk of these kinds of releases.
Okay, got it. So fresher fuel equals more ruthenium-106 equals higher potential risk if something goes wrong chemically.
You got it.
So let's bring this all back to the 2017 event and MIAC. What specific activity might have triggered this release? The sources seem to point towards a particular scientific project, didn't they?
Yes, the leading theory revolves around an attempt, apparently an unsuccessful one in the end, to produce a different radioactive isotope, cerium-144.
Cerium-144. What for?
It was supposedly for the Borexino experiment, which is a neutrino detector deep underground in Italy. Apparently, MIAC had a contract to supply this isotope, signed in autumn 2016, but then the contract got canceled in December 2017, shortly after the ruthenium release.
Interesting timing.
Very. And what's really significant here is that MIAC was believed to be basically uniquely positioned to extract the cerium-144 from relatively fresh spent nuclear fuel.
How fresh?
Maybe only 2 or 3 years old?
Linking back to the age of fuel point.
Exactly. And this is crucial because remember, younger fuel has a higher ratio of ruthenium-106 compared to another ruthenium isotope, ruthenium-103, which has a much shorter half-life.
Okay, so the ratio changes over time.
Right. And the isotopic fingerprint, the actual measured ratio of Ru-106 to Ru-103 in those environmental samples collected across Europe in 2017, that ratio was consistent with relatively fresh spent fuel.
So the radioactive signature itself pointed to young fuel being processed.
Yes. It acted like a forensic clue. It strongly suggested the source involved processing fuel of a specific younger age, which heavily points towards facilities known to handle that kind of material, like MIAC, especially if they are trying to extract something like cerium-144, which also decays relatively quickly.
Wow, okay, that isotopic fingerprint sounds like a really compelling piece of evidence, even if it's circumstantial.
It's considered very strong evidence by many scientists.
So what do the official Russian investigations say about this specific theory, the link to cerium-144 production from fresh fuel?
Well, while the Russian members of the International Commission looking into this acknowledged the findings from the French IRSN and others, they maintained their position. They stated that inspections they carried out at MIAC found no evidence of any operational problems or anomalies that could explain such a release.
So still denying it was MIAC.
Still denying MIAC was the source of that release, yes. They also floated an alternative idea,
That was.
suggesting maybe some kind of rare meteorological event, like a freak weather pattern, could have somehow concentrated and transported ruthenium-106 from a totally different unknown location to the South Urals region, basically creating a false signal there.
That sounds less direct.
It's certainly a less direct explanation than a release from a known facility in the area that handles this material. And it's important to add that in 2019, several independent European scientific groups published papers presenting what they called clear evidence.
Based on what?
based on their refined atmospheric modeling combined with that isotopic analysis. And their conclusions firmly pointed to the southern Urals, the region where Mayak is located, as the origin of the release.
Okay, so it really does sound like a strong scientific consensus outside of Russia pointing squarely at Mayak, or at least that immediate vicinity.
That seems to be the case, yes.
And our sources also mentioned, didn't they, the difficulties in actually getting a completely clear picture from within Russia itself.
Yes, that's a significant factor here. The chances of a fully transparent, independent domestic investigation face some pretty big hurdles.
Like what?
Well, first, Mayak is located in Ozyorsk. That's a closed administrative territorial entity, basically a closed city.
Meaning you need special permission just to get in.
Exactly, even for Russian citizens. That naturally limits access and scrutiny. Plus, there have been documented reports over many years of, let's say, government pressure and even harassment targeting nuclear critics or independent environmental groups within Russia.
Making it hard for anyone to investigate freely.
It certainly creates a chilling effect. Critics have apparently been accused of, using nuclear issues for political gain, and some have even faced risks of prosecution.
Right.
So the key insight here, perhaps, is that even these kinds of seemingly low-level radiological events that cross borders really highlight how crucial open communication and strong international cooperation are for building public trust and ensuring nuclear safety.
So if we were to sort of boil this all down, try to summarize this deep dive for everyone listening, what are the absolute key takeaways from the 2017 ruthenium event?
Okay, the essentials are probably these. First, autumn 2017, there was a release of ruthenium-106. Second, while it was detected at very low, non-hazardous levels across most of Europe, the estimated total amount released was significant.
Meaning it was likely dangerous near the source.
Potentially, yes, within a few kilometers. Third, the overwhelming scientific evidence, the atmospheric modeling, the isotopal fingerprint strongly points to the origin being in the South Urals region of Russia.
And the Mayak facility is a prime suspect.
Mayak is the most likely specific source, yes, although this hasn't been officially confirmed or acknowledged by Russia. And finally, the theory that links the release to a mishap during an attempt to produce cerium-144 from relatively young spent fuel. That provides the most scientifically plausible explanation currently available.
Especially given those isotopic ratios found in the air samples.
Exactly. That's a key piece matching the theory.
And yet, despite that strong scientific consensus outside Russia, the complete, unambiguous picture is still a bit murky, isn't it? Because of those challenges in investigating fully within a closed system.
That's right. There are still uncertainties, and the complexities of investigating incidents like this, especially in closed environments, are undeniable.
So maybe a final thought to leave people with. Something to chew on.
Yeah, maybe think about this. What are the wider implications when radioactive material crosses international borders, even if the immediate health risks seem limited far away? What does an event like the 2017 ruthenium release tell us about how vital transparency and real international cooperation are when it comes to nuclear safety and just protecting the environment generally?
Hmm.
And maybe also, what challenges does it show we still face in being able to effectively track, understand, and explain these kinds of environmental releases? And looking forward, what might we need to do differently to make sure future events, if they happen, are monitored better and explained more openly?
Lots to think about there. It really feels like a complex puzzle, like you said,
Yeah.
with some key pieces still frustratingly missing.
Absolutely. A modern mystery with echoes of the past.